Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to be here introducing Ross McElroy. Ross did an internship with us 2007, so 3 years ago, and it helped us build the Helios operating system. That was where we took Singularity and made it run on multiple cores and multiple I/O devices and pulled it together as a single operating system. He did the very hard work of being the first one to get Singularity to run on an ARM-based I/O processor, and did a fantastic job with us. And then he just finished up last year's PhD at Glasgow, and he's now at Cambridge, the MSR Cambridge, doing a postdoc. But he's here to talk about his PhD work, so take it away, Ross.
Thanks, Galen. So yes, as Galen said, this was my PhD work with my supervisor, Joe Sventic at the University of Glasgow. So I wasn't in Microsoft writing a JVM. This is work which I was looking at how to make heterogeneous multi-core architectures more usable by lay mainstream programmers, so i.e. nobody that's in this room, but people who might use our product. So I'll kind of motivate why I think this might be an interesting problem to look at, heterogeneous architectures, then talk about a couple of the design decisions we made in Hera-JVM. Then I'll go into some more detail into the implementation of how I actually went about executing Java code on these heterogeneous architectures on the Cell processor, which was the heterogeneous architecture which we looked into. Then I'll talk about some extensions to that where we looked at using program behavior to try and automatically place threads on the most appropriate core types. And get performance that way so that the users didn't even need to specify the partitioning of their program between the cores. And finally, I'll conclude. So what do I mean by heterogeneous multi-cores in the first place? Well, I'm sure you're all aware CPUs are currently becoming more and more multi-core. And there's the kind of question of whether all these cores should be equal. At the minute, most commodity systems, all the cores are homogeneous and equal in most senses. But there's a couple of good reasons why you might want to have heterogeneity in the processors. And I'll talk about a couple of these. So first off, you could just specialize some of the cores. So as Intel's going on, has more and more transistors and throwing more cores onto the system, it might get to a stage where really, from commodity point of view, there's nothing much that the user-level applications, they can't use much more cores. They've not got enough parallelism available to them. And so instead of just throwing the same core onto the computer, what you could do is throw a specialized core for certain functionalities. And then even if the user-level application is even single-threaded or doesn't have enough parallelism to use the whole system, it could migrate to those specialist cores when it's doing a particular type of workload and gain some benefit in that way. And so as you end up with more and more cores, this costs you less proportionately. So this might be an interesting way in which we see heterogeneity coming into the mainstream architectures. Another relates to Amdahl's law. So I'm sure you're all aware Amdahl's law states that even if you have a small amount of synchronization of serial code, synchronized code, in your parallel system, it can limit the maximum amount of parallelism you can really achieve. And so one way to get lots of parallelism is to have lots of very simple cores, but that means when you end up hitting this synchronous bottleneck, you have to run on one of those wimpy cores, and that's going to be very slow, and that's going to limit the amount of parallelism you can gain from all those cores. So why not have two different types of cores? One which is a much more complex core with more instruction level parallelism, and a bunch of other smaller RISC-like cores which you can throw all the parallelism to them. And that kind of makes better use of the silicon in this case. And there's a good analysis by Helen Marty about how heterogeneous architectures can help in this case with Amdahl's law. So at the minute, these architectures are really limited to specialist domains. You can see them in network processing with the Intel IXP, and gaming or multimedia and scientific computation where the IBM Cell is being used. But they're not really in commodity systems at the minute. But I think that may change, and the reasons that may change is two things really. First is GPUs. GPUs are becoming more general purpose. There's more ability to run general purpose on these GPUs, and they can give you very good performance for certain type of workloads if you know how to use them well. And there's a number of initiatives where the GPUs are ending up being put on the same processing die as the CPU itself, so AMD Fusion and Sandy Bridge. They're not necessarily the best GPUs at the minute to do general purpose stuff on, but this may change. And once you end up with these small GPU type cores and your general purpose core in the same CPU, you end up with something that looks quite similar to the IBM Cell. And so the other kind of convergence factor is the many core architectures, and these are just research architectures really that are looking at this at the minute. But as you throw, as I said, as you throw more cores onto the system, Intel might want to look at specializing some of those cores just to give them a better balance and a better ability to do certain workloads. So this is where why I see it as being an interesting area to look at. So what are the challenges? Well, when you're developing an architecture for one of these, developing an application for one of these architectures, you need to take your application, say it's a bunch of threads or whatever, and you need to decide ahead of time which bits of the code are going to be run in which of the different architectures. So already you've kind of limited your potential portability, and you've focused yourself on one particular architecture. And you need to have quite good knowledge of that architecture to be able to figure out which bits of these different programs are going to work well in which different architectures. Yes?
There seems to be a hidden assumption that the heterogeneity is not just in the microarchitecture, but also in the user-visible architecture. I mean, you could have a chip that has 486s at one end and Pentium 2 at the other end.
Well, yes, okay, so I'm kind of looking in that space where there's more heterogeneity in the instruction set architecture as well as the other area. But even if there's not, I suppose you can then look at user level thread migration and scheduling decisions, but there's still the kind of different performance capabilities of the different cores, and if you don't know what they are, that may affect you. And so some of the approaches here might be useful there for either the operating system or the runtime system to be aware of, even if it's not instruction level parallelism. So I'll talk a bit about that. So, so once you do that, if it is a different instruction set, you're going to need to split out your code between those two different architectures, and there's going to be a different build environment, typically, different code environment, different set of libraries, typically. And then you need to add support code to deal with the fact that a thread's going to be migrating between different cores. This core might want to do some file access, which is not allowed on the secondary core, so you need to add some support code there and support code back on the main architecture to deal with these facts. Then you kind of link it all up together, and you end up with usually what looks like almost two separate applications. And typically in these types of architectures, they're going to have to communicate explicitly by moving data between the different memory hierarchies on each of the different core types. So you have explicit data copying. You end up with something that looks a bit like a distributed system with a very fast interconnect between them. And it's not very... this is fine for specialist programmers to do, and they can do it very well and create very good programs. For a mainstream programmer, they're not going to go through all this process to create something that can take advantage of the heterogeneity, I don't think. Especially because at this stage, once you've reached this stage, you've lost any portability, really. It's very difficult to go back and decide. You need to almost redesign your application at this stage if you want to move something from one core to the different core. And you need to have a lot of knowledge of what those architectures are doing. So this is where Hera-JVM, this is why we were interested in looking at this system. So the kind of fundamental design decisions behind Hera-JVM, as I said, it's an approach where we're looking at mainstream programmers who don't want to be dealing with this at all. They just potentially want a bit of performance benefit from being able to run on a heterogeneous architecture, but don't want to have any of the worries associated with doing that. And so with Hera-JVM, we're kind of hiding this heterogeneity completely from the application developer. We're presenting them with a homogeneous virtual machine interface. And the same Java code can be run on any of the heterogeneous core types. That's our philosophy. And so the developer doesn't need to worry about certain instructions not being supported or certain operations not being supported. And it's the runtime system's decision about where the code runs. The runtime system is aware of what resources it has available. And I'll talk about how the runtime system can become knowledgeable about how the application performs, and therefore it then makes up the decisions about moving application threads between the cores and migrating and deciding which cores are the most useful to run it on. And finally, dealing with this explicit data copying and unusual memory models inherent in these architectures usually, our model is that there's a shared heap, and it's up to the runtime system to keep that consistent, and in our case, keep it consistent with the Java memory model so that properly synchronized parallel applications will continue to work in this architecture, even if there's no cache coherency in the hardware itself. So the architecture we looked at was the Cell processor, which here's a floor plan of the Cell processor, and what I wanted to point out was that it has two different types of processors which are very different. So if you're not aware of the Cell processor, it has one PowerPC, or power processing element processor, which is a fairly typical, although slightly wimpy, PowerPC architecture. It can run the operating system, it can run standard PowerPC applications. The Cell also has 8 of these so-called synergistic processing engines, or SPs, which are very simple RISC designs that are blazingly fast at floating point and SIMD type instructions, multimedia type workloads, but they have a very unusual architecture, completely different from the PowerPC. So I'll go through some of the differences they have here. Yes?
Before you jump there, another devil's advocate question.
Yes.
On some benchmarks that are not particularly fake, the typical slowdown for going to Java was 20 to 1.
Going from C to Java, you mean?
Yeah, from
Java C or something.
Java. And in fact, it was the AES competition.
Yes.
And a guy from Sun came and kicked an own goal by showing a median slowdown of 20 to 1. Can you beat that with your parallel speedup? Can it be applied to
so the best speedup I got for running a parallel benchmark on, it was 6 cores because the PlayStation 3 you lose 2 of them, was 13 times, which I'll show in the experiments later.
6 cores give you 13 times speedup?
Yes, compared to the PowerPC.
I'm sorry.
So, but that's the kind of I'll get to that. But yeah, I mean, there's the obvious question of whether Java is fast enough. In some cases, Java and high-level languages, you can get very good speedups if you can do the compiling right. But that's not the question I'm looking at here. I've taken a high-level language and we're trying to speed up something that's already written in a high-level language, not compare it to C.
I'm old enough, I think C is a high-level language.
Yeah. So getting back to why the SP is different, so it's got a completely different instruction set from the PowerPC, much more focused on kind of floating point and has multiply, accumulate, and these types of instructions available to it. It doesn't have any operating system support. The operating system runs on the PowerPC, and the SPs have no control over doing paging or any of these types of issues. If they want to have any interaction with the operating system, they need to go through the PowerPC. Also, most unusually, and in the case of Hera-JVM, most bothering, it doesn't have a hardware cache. Instead, it has explicitly mapped local memory, scratchpad memory it's sometimes called. So it's got 256 kilobytes, which it can access, and it can only access this local memory. It can't directly access the main memory. If it wants to access some data that's in the main memory, it needs to signal its own on-chip DMA engine to perform the copying of that data across from the main memory into its local memory, and vice versa. So there's no cache coherency between the data when it's in here and in here, obviously, and you have no hardware cache support. So this was one of the main challenges in creating Hera-JVM. So going back to the kind of goals of Hera-JVM and how this changes on the cell or what needs to be done to get this working on the cell. So to hide this completely from the application developer, we want to support the full Java specification in either core type. So this means it appears to run anything. And if there's something that it can't run, for example, system calls or native methods because there's no operating system support in SPs, that's hidden transparently using migration or proxying to the operating system, to the PowerPC. And you obviously want that to happen as little as possible. So in this case, things like object allocation, exceptions, file handling other than the system call parts of it, they all occur on the SP cores. The runtime system needs to be able to do the decisions of when things are migrating. So in our case, we allow transparent migration on any method invocation or any method invocation that's not marked as non-migratable. And so any method invocation is a potential migration point. And then to share a common heap, well, we need to use software caching to hide this explicit memory of the architecture. But because we're in a high-level language, we can use some tricks to try and avoid all the overhead that will entail. And I'll talk about that in a minute. And also, we need to keep in mind coherency operations, synchronization operations to try and keep the Java memory model, keep with the Java memory model. So how do we go about creating this for the cell? Yes?
Are you going to support volatile locations?
Yes. Yes.
Are you going to talk about how you do that?
Sure. I'll talk about once I've talked about the software caching, I'll show you where volatile comes in. So for two...
Is to ask this. Maybe looking back, this is not really a criticism. I'm just wondering if Java's threads are sort of natural. I mean, there's lots of advantages to learning write in one language and leaving it up to the runtime system to migrate things back and forth and put things where they belong. But that doesn't necessarily imply that a Java programmer wants to use, java.lang.thread to represent parallels. It's a pretty heavyweight notion. It's a pretty unstructured notion.
So, yeah, I mean, this is a kind of design decision in this case. I mean, things like accelerator or things like that are a different model where you're expressing the parallelism in a different way, in a more data parallel way or something like that. This, we're trying to be able to support the threading that they would do normally for a normal Java application. Now, if on top of that you have some kind of library, or even if there's some Java work in auto parallelization or things like that, then this could go on top of that. That could go on top of this. Sorry.
Yeah, I was actually thinking maybe a little less different than that. That a lot of multi-threaded Java applications are in fact using a pool of worker threads and are really programming a higher level of abstraction. It's not clear that you necessarily want your JVM dealing with the worker threads. You might want to be working, that one level up, moving the lightweight things over to the SPs and back. But you're really doing it at the pure Java language level.
Yeah, it's a thought. I mean, migration's not hugely costly. Whether it's, I think the migration cost would be the same whether it's a thread or not. But you may be able to extract some more knowledge out of the fact of the higher level, the way the parallelism expressed, which might be useful in that case. Yes, yeah, that could be some interesting future work. So to create this system, Hera-JVM, it's based on JIKE's RVM3. So that's a Java in Java virtual machine. So most of the runtime system itself is written in Java, which confers some advantages, as I'll show. And it also supported out-the-box PowerPC and x86. So the PPE core is automatically supported by JIKE's. We just needed to add support for the SP cores to get things running. Yes?
They avoid all the problems with byte sex, because that usually breaks code when you run it on big endian and little endian.
Java is
really byte neutral?
Well, I mean, the two architectures are both big endian in the cells, so that's fine. But I mean, I think Java's specification is that things are big endian, and whether the runtime system treats them as little endian, when it exports some kind of data, it needs to be always in big endian. But it's up to the runtime system how it does it. I can't remember seeing any thing in JIKES that was dealing with little endian, big endian particularly. But all the operations were happening in the native endianness. So JIKES, it's a non-interpreting JVM. Everything is JIT compiled. There's 2 JIT compilers. We only look at the baseline compiler. So I wasn't writing an optimizing compiler for the SP, so it would be too much work. So you have basically this kind of structure where you have an assembler and a compiler written in Java itself, and some low-level assembly, which is part of the JIKES RVM. And then on top of that, everything else is Java. So the runtime system, the majority of the runtime system is written in Java and would be bootstrapped to native code beforehand. So to support the SPs, we just really had to add the SP compiler, assembler, and some additional low-level assembly. And things here might be the software caching and things that I'm going to talk about. And then we basically end up getting the runtime system for free in some sense, the more complicated parts of the runtime system at least, such as object allocation and memory management, file handling, class loading, things like that. And you basically end up with having the same philosophy right down through the stack. So the runtime systems, you're running the same code on both cores in the same way as the applications running the same code on both cores. And so this kind of gives us a nice way of looking at things. So once you have support for executing code on both cores, you need to be able to support migration between the cores. So as I said, any method invocation can be a migration point. It can be triggered either statically by annotating a method and having some part of the method annotated to statically do that migration, or the scheduler can do things dynamically, and there was a couple of different ways we implemented the dynamic migration, such as obvious flags and things like that. But basically any method other than those marked as non-migratable can be migrated, and syscalls and native methods always migrate if they're on the SP back to the PowerPC, as I said. Now, one of the issues with this architecture was that the stack frames are laid out differently on the 2 different architectures just by virtue of how different the architectures are. And that means that once you've migrated across, once you return from that migration method, you need to return to the original core you were on, which has a couple of implications that I'll talk about later. But to do that, we put a migration marker on the stack just so that we know that, and that also allows us to allows GC to interpret the stack frames correctly. Yes?
It seems like the native method choice would lead to sort of naive performance topologies that maybe you had to mess with, right? So maybe the JIKES implementer goes in and cheats and says, I'm going to do memcopy in assembly because it's going to give me some huge win. So
in JIKES, luckily the philosophy was that almost as much as possible is in Java, not native method. So they didn't do those cheats. They have magic methods, they call them, which are basically assembly hand-coded methods. That's fine with us. We can deal with that. Now, one thing that was dealt with in that way is, as is often the case in these Java runtime systems, is the math library, where they just do native calls to the math library. So in that case, we did kind of cheat, well, not cheat, but implemented the math calls as native assembly so that you don't end up killing yourself whenever you call square root or power or anything. Yes?
Naively, I'd say, if you want to get performance by native methods, you want to run on the what you call it, synergistic ones, right?
Well, yes, I mean, so it's not a matter of performance, it's just we can't control what the native methods are doing, and we can't compile them. And typically a native method will be making some operating system call anyway, so it's going to need to run on the PowerPC. The math methods are an exception to that. And also just handling the ability, so you have this limited amount of scratchpad memory that your native method would need to be in, and you want to make, and all its data would also need to be in there as well. And you need to avoid messing up the data that you've got in there for the JVM and things like that. You wouldn't be able to control that. So something that we avoided, and it didn't seem to affect performance too bad. So now talk about the software caching that we had to do to deal with the explicit scratchpad memory on the cell. So as I said, data needs to be DMA'd using this on-chip DMA engine. Now, I mean, this is not an external DMA which is going to cost you millions of cycles to program or whatever, it costs. It's relatively cheap for a DMA engine to program, but it's not like a load instruction. And the DMA is actually relatively fast. The problem is that actually setting up a DMA is relatively costly, and both in terms of cycles and instruction count to do that. So what we want to do is try and do as few DMAs as possible, pulling in as much potentially useful information as we can with every DMA. And so we took advantage of the high-level knowledge we have embedded in the Java bytecodes with the typing information. So when we access an object, we know we are accessing a particular type of object and a particular field in that object, and therefore we can pull across, as I'll show in a second, the full object on the assumption that you're going to be accessing some of the other fields in that object subsequently. And similarly, for arrays, you know specifically that you're accessing an array, not an object, so you can treat it differently, cache a much bigger block of the array. And I'll talk about coherency and synchronization and volatiles. So I'll go through a kind of demo example of how this works, just to give you a clearer idea. So main memory here, local memory here, this is the data for an object. So fairly typical, so up here is the Java bytecode. We have a get field operation, so it's wanting to get a field from that object. And alongside that, you have the type information, the offset of that field, and the address will be on the stack for that object, the data for that object. So that translates into typical kind of software caching technique of hashing the address into a cache table. But notice we're hashing the address of the object, not the address that we're actually accessing, which would be the offset to that address. This will point to a particular entry, and we'll see that it's a cache miss in this case. So this operation would be inlined. Now, since it's a cache miss, we'll hit a kind of out-of-line cache filling operation in the low-level assembly that I was talking about. So we now want to do a DMA copy of this object into the local memory data so we can access it. So we take the address, and we allocate some local memory and the size of that particular type, copy it across, and then we can update the cache table and do the entry as required. Right, and then along comes a set field to the same object. The same thing happens, we do a hash, and this time we hit the entry in the cache table, and we can do that update directly without going through any of the slow path there. Now, there's some subtleties to this, one of which being subtyping. The set field or get field operation, the type that is statically associated with that is the type statically associated. The object may be a subclass of that particular object, which generally means that the object will be larger, it'll have some more fields at the end. Now, that's okay for the first instance of the copy because we were getting a field in the super type, so we're not going to go over that boundary. But in this case, if we hit the cache, we may be trying to access something different. So alongside the address in the hash table, we also keep the size of what we pulled across, just to make sure, and we check that when we do the cache hit, and if it's not big enough, we're going to need to do another cache miss operation, pull it all across again. Now, as I'm talking about, we've now ended up with this situation where things are not coherent with main memory. And this is an issue, obviously, and we don't want to do flushes every single time we do an update, because that's just going to absolutely kill performance. So we take advantage of the Java memory model, which states that things can remain inconsistent up until a synchronization point. So a synchronization point in this case is either a kind of monitor exit or entry, which is the bytecode for the synchronized blocks, or, as you said, a volatile field access. And so if you do a volatile field access, this is also a synchronization point. You need to do this. Yes?
How well do the existing applications follow that model?
So this is something that I was very surprised about. I thought that there would be inconsistencies that would crop up in normal applications. They're just not following it. But I did not see any particular data races. Things seem to be written in a relatively data race-free environment, which is, yes?
Getting back to the subtyping issue,
yes.
You consider just on the get pulling in the whole object?
Well, the problem with that is that to know the size of the object or the type of the object, you need the header of the object itself.
So it'd be 2 rounds.
So it'd be 2 round trips. You would need to pull across the header. Now, what potentially you could do, and I thought about doing, was after you do the first get normally, and then check the type to see if it is what you want, and then pull the rest across if need be. That might be a potential optimization.
Just on the setting, you do need per field dirty bits, right? Because when you put this back out of the
So what we do here, so I'm kind of simplifying things slightly. It's actually a write-through cache. When we do a write, we actually do set up a DMA to do it across, but we don't block on that DMA. And then what we do is we wait for a monitor exit. When a monitor exit hits, we block on all DMA writes to ensure that they've all been written out. I did play about with a write-back cache where you had a log of fields that had been accessed, and when you hit one of these, you would write them all out. And it helped significantly with some I was just using a kind of, if it was going in a sequential way, then it would log this, and it would considerably help the write-back performance, but it led to issues, and it was very complicated, and it caused bugs. So it's a write-through approach. So this is what it would ensure that it's written back through. And you also have the opposite problem where someone else has written something to that data, but you would hit the cache and not see the update because the update's not been propagated to your local memory. So in this case, it's only monitor enter operations when you're actually locking a field, locking an object. You're doing a locking operation. That's when you need to have the fresh state available to you. And so in these cases, we do a very naive thing and we just simply flush the cache. You could think of much more sensible things to do there. The problem is that you don't necessarily know what you need to flush. It would be nice if the Java memory model stated something like synchronization on an object means that that object is going to be accessed, but of course that's never necessarily the case. And if that was the case, you would only need to flush that particular object. But this is what we had to do. So that's object caching. We also need to cache method code. Yes?
That's a mini question. So JAX has all this sort of thin locking stuff built in.
Yeah.
You borrow a lot of that as well?
Yeah. So yeah, thin locking. So we use the same kind of mechanisms as JITE uses. There are, the PowerPC approach is the kind of lock, load conditional and store conditional approach rather than a test and get. And there are those operations in the DMA engine. Now obviously they're slower than doing the actual instructions, but you can do the same actual synchronization approach.
And is that saving you cache flushes, or is this just...
That's just so that you're ensuring that you're doing atomic lock updates.
Okay,
right.
So
you still need to do the cache flushing after you've done that or before you've done that. Yeah. Because that's only on one cache line, the lock load conditional thing that you know if anything's changed. So method caching, we considered a bunch of different approaches to caching the code of methods. A similar approach to the objects, you could use hashing, but the problem is that collisions are very expensive. We're going to cache the whole method, and so if you collide, you're going to be pulling in methods back and forth all the time. Or single method pointer, single table of method pointers, that's going to be too big. And both of these approaches are very much complicated by virtual method invocation. So instead of doing that, we went with an approach which we called a class table of contents, where we have a small table where there's one entry for each of the classes that has been instantiated by the system, or at least each the classes that potentially might be seen by code on the SPEs. And this kind of exploits class localities. So we have a table here. These are now, at the start, they're always pointing to main memory. And they point to a type information block, which gives you information on the methods of that class. So when you do an invocation, you first indirect through the cache table of contents on the type of object that you are invoking a method on. If that's not cached, you cache that into local memory and pull in this type information block, which has alongside it the addresses of the actual SP native code for those methods and the size of those, so you can do the DMA operations. And so you do the same thing here where you cache it in the method in local memory. So this is a kind of, it's a two-stage caching process, but this is all in local memory when you're doing cache hits, which is exceedingly fast in the SP, so it's not really causing you much slowdown. Yes?
Does that mean that if an application has really very, very many classes, it will cause problems because the table will exceed the local memory?
Yes, it would cause problems.
So I better not run Eclipse, for example.
Well, so what I did here was there's a kind of class loading set of things going on, and I had a kind of two-stage process where a class could be loaded it would be initially loaded for the PowerPC, and then if any of the code that was going to be migrated to the SP, you would look at the classes that would involve, and it would instantiate those for the SPE. So it's only going to fill this table with things that are going to be run on the SPE course. So if you were only accelerating a small part of it, that would be fine. But yeah, this would be a potential problem. You'd maybe want to do something like paging of that or something. But this, it would be a problem in any case, I think, because you would need to pull in some kind of metadata about which methods are going to be there. So this brings us on to what happens when you run out of space for the code cache. So I'll just give you a kind of example of what might happen. This is the table of contents here. It's pointing to a type information block, which points to a method which has been cached. And as you start invoking methods and running code, this kind of fills up. You cache another type information block, you cache some more methods. And eventually you're going to run out of space, obviously. Now, at that point, we obviously want to flush the cache, but we're in the middle of running one of these methods. We don't want to flush the code of the method that we're running. So we need to keep track of that. And we can't just use something like a return address because these methods are being cached. They're going to move about as we go. So what we have is in the stack, in place of an actual fixed return address, we have the index into the table of contents that we went through to get to this method, the index into the type information block that we went to, that is that method from that type, and that gives you this arrow, and then the return offset off of that method. So now we know where we are by following these in directions. So we can now flush the cache and compress. We're simply using bump pointer allocation for this cache. You could do something more sensible. We're using bump pointer allocation, and so you move everything back to the start so you can start again. And then this brings you to the question, now you're going to return from that method, but the method that you invoked it from has disappeared from your cache. So again, the fact that we have this information at the top of the stack, we can do exactly what we would do in a method invocation and cache that method whenever we are returning in the same way as we do in an invocation, and we end up being able to get the method there and the return address, obviously. So offset. So that's kind of how we went about getting things running on the SPs. This is some evaluation. So this is Microbenchmarks from the Java Grande section 1, just to show you the vast variation in just simple Java operations. So things like arithmetic, local operations, casting, looping, anything that doesn't touch the software cache absolutely flies on the SPs compared to the PowerPCs. Higher is better on the SPs, lower is better on the PowerPCs. Anything that touches the software cache involves much slower operation, and this is exacerbated even more if, in these cases, your working set's fitting in the cache. It's exacerbated even more if it's not. Yes?
Why is the speed up on math so disappointing?
Because I don't know. It could be, I think it's because, as I said, the math is done in native code on the PowerPC as well. And so you're maybe just not seeing the advantage that you would because I'm kind of hard coding it in assembly. There's also the question of math is going to be doing some stack manipulation, some heap manipulation type things in the Microbenchmark to do the math operations. So that might be hitting us as well. And method invocation as well, which some of the others won't be doing. Method invocation is slightly slower. And so synchronization, of course, is slower on the PowerPC and the SPs as well. So I also looked at a bunch of more real-world macro benchmarks, shall we call them, from Java, Grande, Spec, and Dacapo. And again, you can see even in these macro benchmarks, there's a wide variation in performance depending on what you're actually doing. So these scientific examples that you would expect to run well in the SP do run well in the SP. Multimedia type things also run very well in the PowerPC. Things which are dealing with memory, such as SQL database type things or coded things, are running much slower. And compress here, although it seems like it would be quite an arithmetic-y type thing, which is fast, the arithmetic is relatively simple in this compression technique, and so it goes very quickly, but there's a very large working set of stuff that you're compressing, so you're ending up doing a lot of caching operations there. So this is all comparing one SPE to one PowerPC, but as you saw at the beginning, we have 8, or in the case of the PowerPC that I was looking at, 6 SPs. So for those that can parallelize, those benchmarks that can parallelize, if you can run them on the SPs, you can get massive speedups in any case, whether your application runs well in the the SP or not. So it seems to scale quite well. Yes?
I'm surprised Monte Carlo speeds up so much, because most Monte Carlos have pseudo-random that's totally sequential and kills your algorithm.
Yeah.
So how do you get out of that?
I think the Monte Carlo version here batches up some of the pseudo-randomness ahead of time, and so you end up not having synchronization every round. So that was execution on the SPs. Now we need to worry about, in that case, I was just explicitly deciding whether it should run in the SP or the PowerPC. So I'll talk a bit about some work I did on exploiting program behavior to try and do that automatically in the runtime system. So a lot of previous work on this is kind of assumed that there is simply a fast core and a slow core in heterogeneous systems, and you run the compute-bound stuff on the fast core and the memory-bound stuff on the slow core. Seems to work generally very well. But in this case, this is just not the case. Like, the SP cores are much better if it's an arithmetic, but PowerPCs are better if it's memory access. So your performance is very much going to depend upon the behavior of the code itself. And so that kind of affected our approach of, let's try and analyze the performance and track the performance in the runtime system. Track the behavior of the program in the runtime system and use that information to make decisions more appropriately. So we came up with a set of behavior characteristics, which are characteristics that describe what code does. They have no particular relation to a particular type of processing core or anything like that. They're portable, but they allow the runtime system to make some decision about where that code should be run. So these are things like integer code or floating point code, sequential data access, things like that. The programmer could annotate their code with relatively easily if they know the code. We looked at different ways of doing this, either explicitly annotating methods, which is what I'll talk about today, or we also looked at having the runtime system dynamically monitor some of the behavior, which I've not got time to talk about today, but it worked relatively well as well. So as a kind of example of how this might look, this is a kind of contrived example of a class which is reading an encrypted XML file or something like that, and it first calls decrypt on it, obviously, and then parse. And what decrypt does is it's a block-based cipher, so it does each block of decryption. And there's a bunch of arithmetic code in the next block code. So the developer could quite easily see that and create an annotation saying that this is arithmetic type code. And similarly, the parsing is going to create a bunch of XML objects, so it's an object access type of code. And you notice, so what happens is as the thread goes through the different phases, it will be marked with these behavior characteristics. So when it hits decrypt, because it's mostly doing next block, it's going to be mostly arithmetic code behavior in the terms of the runtime system. And when it hits parse, it's going to change phase and be mostly object access and as what the runtime system thinks about it. And you could have multiple of these annotations on the same method. There's no reason for just having one. You then use a fairly simple cost model to decide which core would be the most appropriate to run based on the behavior characteristics that apply to a particular thread at a particular point in its execution. And so we just create a per core cost model based on the microbenchmark, what the microbenchmarks tell us about the performance of the different types of the cores for each different behavior characteristic. So when we're looking at the microbenchmarks before, these seem to be the three main characteristics that mattered in the cell. And so, for example, in arithmetic, the SP is about 4 times faster than the PowerPC, so you give it for cost 4 times less, vice versa for object access, large working set. And we simply sum together the costs. So, for example, if the thread had both arithmetic and object access characteristics, to evaluate which core would be the most appropriate, we'd sum together the costs, and the SP core would be the most appropriate in this case because it has the lower cost. Now, that's how you get a cost at a particular point in time. What we then do is we sample the costs and use exponential moving averages and hysteresis, which I'll talk about in a second.
Is it weighted by instruction frequency, or how do you, or just by the annotation alone?
So, for the sampling approach, so we use 2 approaches, which I'll talk about just now, and this might explain it better. So one approach is, as you say, you simply, when you hit an annotation, when you hit a method that has an annotation, you reevaluate the cost functions and decide whether you want to migrate, right? So if you have the previous example we had there with the read file, decrypt, next block, etc., what's going to happen is, this is a call trace. Your next block is annotated with arith, and pars is annotated with object access. And if you do this approach, what's going to happen is that every time you hit next block, you're going to migrate across the SPE, and you're going to migrate back. Now you can see the problem here. You're going to do lots of migrations which do not much useful work in between, and your cost of migration is going to be a factor. So this approach worked very well if the developers knew, if you could figure out where to put the annotations properly, but if they were put in wrong places like this, which actually make more sense because it is actually the next block method that is doing the arithmetic operations, it's going to kill your performance. So we saw, for example, a 50x slowdown in the ray trace program doing this. So the second approach is to, rather than reevaluating the cost every time you see an annotation, reevaluate at fixed time intervals, so in this case at timer tick scheduling epochs. So every time the timer interrupts, you look at the current method that's executing, or you look at the set of behavior characteristics that apply to the thread based on the current method that is annotating, and the call trace of any methods below. That's kept track of dynamically. And you'll work out the cost. And so here we have, I'm just going to show, it's a migration target score, which is just the cost of one minus the other. So in this case, you're simply looking at which cores. If it's higher, it's going to be on the SPE. If it's lower, it's going to be in the PowerPC. And we use hysteresis to prevent doing lots of migrations all the time again, and exponential moving average. So it will kind of bump up a wee bit the first time you hit it, the second time it hit it, bump up a bit more. And that's going to signal a migration is going to happen, and it'll bump down here.
So, but how do you calculate the actual cost? Is this, do you look at the instructions that are getting executed, or just some kind of annotation on the stack, or?
It's just, so at each scheduling epoch, it's just what is currently happening. So it's nothing to do with the number of instructions that have happened or anything. It's, as you go through the methods, you will the thread will pick up a set of behavior characteristics based on the annotations on those threads. And so you have those behavior characteristics, and when you schedule it at that particular point in time, you have those behavior characteristics. That's your current cost.
Based on annotations and call stack.
Yes, in some sense. Although we don't look at the call stack, we're keeping a bitmap, but yeah, effectively. And that's why we're doing this kind of exponential moving average, because you might hit a rogue sample somewhere. You might hit here or something like that when you actually want to hit somewhere else.
So then you bump this up if you're saying, oh, it seems like I'm doing more arithmetic, and you bump it up.
Yes,
and then you
exactly.
do it again next time.
Yes. So going back to your instruction count thing, the runtime monitoring approach we looked at was actually counting instructions, but that was to work out what the behavior characteristics were. So it was a kind of two-stage process. You would count the number of each class of instructions that were happening, and that would give you the behavior characteristics of that thread at that particular point in time, and then you still use this approach after that.
It's like a summary.
Yeah, it's a summary of the behavior. Yeah, exactly. And hopefully this tracks quickly enough with, I mean, phase changes that you want to invoke a migration upon are going to happen relatively slowly compared to scheduling quantums anyway. Otherwise, you're going to lose your time just doing migrations. So once you've hit this point here where you want to do a migration, here, where you want to do a migration, what are you going to migrate? You don't want to just migrate the next method, because then you're back to the same problem beforehand. You're right, doing one method, which is just going to kill you. So we had an approach which we call targeted migration, where when you invoke a method, you put on the stack also the current scheduling quantum when you invoke that method. So this method was invoked in scheduling quantum 1. These were invoked in scheduling quantum 2, 3, 2, 1. And then when you decide you want to do a migration, you traverse the stack and find the first method that was invoked in a previous scheduling quantum from the one you're currently in. So in this case, the decrypt method. And so then you know that at least for the previous execution of that method, it took at least one scheduling quantum to complete. And so it's a relatively long-lived method. And this seemed to work surprisingly well, this simple approach. So in this case, we mark decrypt as a method which should be, we're effectively putting a run-on SP annotation or mark on that method, so that whenever that method is ever run in the future, it's going to cause a migration to the SP core. And in this case, this is what would happen. So we did. Sure.
It's not at all surprising that you're collecting this information and using kind of a weighted history and whatever on sort of a per thread basis. How is this thread behaving?
Yes.
It's a little more surprising that your scheduling decisions, your migration decisions are being done on a per thread basis rather than as a global resource allocation problem.
Yes. It's partly the challenge there is simply the fact that when you migrate something across, you need to come back at a particular point. You're forced back onto the original core after that method completes. And that's really the reason for doing it this way. I also had a kind of quick look at using this approach in a NUMA architecture and using behavior characteristics to kind of reason about the communication between threads and do thread scheduling that way. And in that case, we could do a much more dynamic global idea of which thread should be on which cores and integrate that into the scheduler, because we could move it at any point we wanted.
So in the extreme, right, I can certainly dream of applications where all the threads are doing the same thing, and there's enough of them that you should run some on the SPs.
Yeah.
But if you do it this way, they'll all want to be on one or the other.
I think you need something in the scheduler as well as this. I think you'd want to incorporate this this history information, or this probably you'd want to incorporate this decision here when you hit this migration marker. You then, and that was something I could have done. It's just that I didn't have time to do it. But at that point, you're in the scheduler, and you can decide, right, actually all these SPs are fully taken at the minute. I'll just run this on the PowerPC. I'll not actually do the migration. So you could do that.
So one thing I didn't understand is how do you avoid the calling the next block on the SP and then going back to the PP as you return, right? You said you always have to go back to where the caller was.
Yes. In this case, we're migrating decrypt though.
I understand. But
At this point, we're not going to do a migration. We've just.
Back and forth. Oh, you're not migrating?
No, we're not. We're not going to. We're doing a sampling-based approach, so we're not going to do a migration decision every time an annotation tells us that it might be a good idea. Only when the collective knowledge of that annotations gives us confidence that there is a method that is useful to migrate.
So this is sort of the learning.
Yeah, this is a kind of learning phase, and then here we hit it. So obviously in this case you need to have some kind of repetition happening in your application for this to be useful, but in our case that seemed to work. maybe that's just good benchmarks repeat things, I don't know. So we did this on a bunch of the applications. These are kind of a representative set of those previous benchmarks you saw. Some are good and some are bad on the SPs. And you can see that with annotations, we're seeing the same kind of results. It's deciding quite well whether it should be running on the SP or on the PowerPC. In these cases, these ones are run best on the PowerPC, and there's no real point in running anything on the SPs for these cores. It just doesn't ever run any faster. And we're getting a relatively low, I've got some other results which show the overhead's relatively low in the annotations case. We also, as I said, looked at runtime monitoring, which gives you a slightly larger overhead, but you don't need to do any explicit annotations. It just runs on completely unmodified code. Now, one thing to note is that when we did runtime monitoring, we were only monitoring the arithmetic and data access characteristics, not the large working set characteristics, because that would be a different monitoring technique. And so it works well in most cases, but in this compress case, compress is arithmetic. It's just that it's got a large working set, and that's why it's bad on the SP. So it ended up putting it on the SP wrongly. And what we can do, because we're using a similar cost function type approach, whether we're using annotations or runtime monitoring, is we can use the annotations as well as the runtime monitoring to support each other. So in this case, we're using the large working set annotation alongside the runtime monitoring that we're doing, and we get back to it's now deciding appropriately it should be run on the PowerPC.
But this didn't help, right? So annotations alone seems to be always better than annotations and one.
Yes, but but that's simply because the runtime monitoring is incurring an overhead. Now, what this approach might be good for is if developers get the annotations wrong, which they would potentially. And so what you would want to do is base it roughly on annotations to start with, and feed in it, as we're doing here, feed in any information through annotations that you can't get through the runtime monitoring. And then if it looks like it's been annotated incorrectly, then you can go the correct way. Yes?
So can you talk a little bit to like a general trend here beyond other benchmarks that you looked at that aren't necessarily here? I'm curious if you saw the effect of, let me start over. Let's imagine that at every particular point in the code where you might do a migration, you randomly flip a coin and make a migration, but then you don't have that flip coin. How would your results trend relative to kind of the annotations and the monitoring of those with those annotations? So can you say that that would never work? Random is going to do really poorly.
I would have thought randomness is going to do very poorly because, I mean, are you meaning at any method or any method that you would any long-lived method that you would potentially choose for any long-lived method? I mean, if you're doing it randomly, then half the time you're going to be running with a potentially 2x slowdown if you're running an Antler or something like this. Half the time you're going to be running at normal speeds. So I don't see why you would end up with a 1/5 one out.
So can you do better than that number you're coming up with for kind of back the envelope?
Well, yeah. I mean, so I've not got the results here of what it is running on just the SPE, but in these cases, certainly in the Antler case, running just on the SPE is here. If you were doing it randomly, I would imagine that it would be kind of here, halfway in between. So you're doing better than random. Now, if you're running SOAR, it would be the opposite way around. The SPE is kind of up here. If you're doing it randomly, you'd be around about here, I think. So that's the results. That's just concluding that high-level language gives you some advantages that you can use to alleviate this heterogeneity from the developer, which can be useful if you want to allow mainstream developers to exploit this, not exploit these architectures without doing any work themselves. And behavior characteristics are useful in allowing the runtime system to automatically choose which cores to use. So if there's any further questions, I'd be happy to take them.
So without leaving the Java ecosystem, a programmer that wanted to be aware of this heterogeneity might want features like runtime branches on where I'm running. Use a different algorithm with a different spacing trade-off, performance envelope. It strikes me to be very interesting to sort of see how much you could juice these numbers by cheating and literally running different Java code depending on where the method currently is.
That would certainly be an interesting approach. I mean, certainly for some of these architectures, you'd really, if it's a GPU, a current day GPU or something like that, any normal Java application is not going to run any performance on that simply because it's got branches and things like that. The GPU is going to kill. So you would want to specialize the applications in that case, I think. But yeah, it's a design trade-off, and I think there are potentially some people who would, if there was heterogeneous cores in commodity systems, who would like to be able to take advantage of it with their existing code without doing any work. And that's the people I'm targeting. It's obviously not for people who know what they're doing. Yes?
What's the trend in the architecture of these kinds of systems? Are we going to see the local memory increase in sort of over time?
You mean the size of the local memory, or do you mean the use of it?
The size.
I would imagine that would increase in a similar way as cache increases if people are using local memory things. I think there's less chance of that local memory type approach reaching commodity hardware. What may happen, what we've discussed in various other places, is cache coherency probably never disappearing, but being very slow. And so you might want to use some of these techniques to kind of fake out
So you don't think this is the way that these systems will go forward? You're saying that rather there will be cache smoothing and trades?
I think in commodity systems we can't really do without cache coherency. I don't think Intel's brought out the single chip cloud computer which has no cache coherency, but that's a research thing. And I think Intel would be shooting itself in the foot if it did non-cache coherency. But I think it may be the case that cache coherency is so expensive that you want to treat, in certain applications, you want to treat it more like a local scratchpad cache. And if you had more control.
Effectively, what you're saying here is that if you have a language like Java with a sensible sort of semantics for memory coherency, it does make sense to run this all in software, right? And not.
Well, I mean, if there was good instructions for dealing with the cache and explicitly performing certain operations on the cache, this would be a very good, interesting area to look at, where you kind of allow things to become inconsistent, and as long as you know what you're doing, and as long as you know that at that synchronization point you need everything to be consistent, and you can poke a bit and send an instruction to the cache and say flush out these lines, or update these lines from main memory or from other caches in the system or something like that, then that would be probably be a big win, because you're going to end up reducing the amount of cache coherency messages on the interconnect substantially, which is going to be a big scalability problem as the number of cores increase. So yeah, I think some of these approaches might help there. And that's where a high level language helps, because in C you really have no idea. In Java at least you have some kind of memory model. Something explicit. Yes.
So I had one question, which is the annotation. It seems like you violated that second.
So the annotations.
By putting those annotations, right? Because they're SP.
No. Well, they're not SP explicit. They are program behavior explicit. They are portable, is my reasoning. If you put it on another architecture, they would either still be useful. No, because the costs of those behavior characteristics are in the runtime system, so the runtime system needs to be changed. But the actual application, those characteristics still apply to the application in those phases, whatever architecture it's running on. It's up to the runtime system to interpret those behavior characteristics for the particular architecture it's running on.
Yeah, I guess the one thing I wonder is, okay, I could hypothesize that someone came out with a new bifurcated system that has a different set of trade-offs between the two processors, and are your would I end up with a completely different set of annotations? Or do you think you've got annotations that reflect a set of annotations that are more inherent to job-related computation than they are inherent to the types of instruction sets these processors these systems?
When I was looking at the behavior characteristics, I was trying to look at what are the types of program behavior that can affect multiple different types of applications. So it's things like, the floating point characteristic does say something about it's going to be run in the floating point part of the CPU, but whether the CPU has a fast floating point or a slow floating point or medium one only affects whether you choose that CPU or not. It's not affecting whether the code is going to use the floating point.
Did you think about using profiling to automatically infer these annotations?
Well, the runtime monitoring system kind of does that, except it's trying to do it quickly and not ahead of time. But you could use that and yes, then insert the annotations that way. That was something we thought about, but we thought it was more interesting to look at the case where you're doing it at the same time. So try and make the profiling, the runtime monitoring as cheap as possible so it doesn't interfere too much. But yeah, if you wanted more information and much better profiling tools, you could run it offline ahead of time. That would be a good approach. Mm-hmm. And it would be easy enough to insert the annotations using a bytecode modifier. You could do similar things with static analysis. I think would be an interesting area to look at. Yes?
So could you use the same technique that you used here to handle the explicit local memory of all these SPs in a sort of normal system where you just want to maximize the data locality and the maximization of your cache? So what I'm thinking is that I have 8 general purpose CPUs and they share the memory. Now,
yeah.
I'm going to allocate to them in main memory, like say they have 2 megabytes
yeah,
of cache,
yeah,
2
yeah.
megabyte chunks, all this joint, right? And then
Yeah.
I have the main memory that's shared.
Yeah.
And I use your kind of
Pull things in and out.
implementation to mostly work in my cache and then have explicit callback to
Yeah.
the main memory,
Yeah.
right?
Yeah.
Do you think that would give any gains?
It's certainly an interesting idea. The overhead of doing the copies might alleviate any advantage you get, and the advantage.
Support, I guess, in this
Sorry?
case. You do have more hardware support because you do have the general.
Well, yeah. It's certainly cheaper than doing a DMA. Yes, but it would really, I think, depend on the application. I think if the application had a lot of false sharing, this would give you a big win. But you typically try to write your application to avoid false sharing if you possibly can. And in that case, the hardware coherency is kind of doing it for you, really, as long as you're not. I think it would be a potentially interesting thing to look at for very contended data structures. But in that case, you're possibly not going to be doing a lot of work on them until you copy the data back, and you might end up just. It would be an interesting area to look at, I think.
So
Yeah.
you're not aware of anybody having done such a
No, it strikes me as similar to transactional memory in some sense. They're doing it for a very different reason, but they're doing explicit copies of data and things like that. And they don't get a win in performance, that's for sure. But unless it's massively scaling.
Speaker.